Welcome back to ECE 501B. You may not think it's much of a welcome with a full page of due dates in front of you, but I want you to be aware of what's coming up, and the end of all of that list is our second exam. And that's really 2 weeks from Wednesday, our second exam. You should now have access to practice material for exam number 2, and I think there's also the project is now described in some detail on the website in D2L in terms of what is required. There's even a rubric for the project if you want to know how you're being assessed or measured. But as a reminder, we won't physically be meeting in class next time, Wednesday of this week. So watch for D2L material. Hopefully we will get as far as I'm planning, and if we are, then you can watch the orthogonalization lecture, which is what will be our next contact. We won't physically see each other, but you can now look at that information, and hopefully today's material will set that up. We'll learn about orthogonalization and breaking up vectors into orthogonal decompositions. So homework number 4 is due at the end of this week on the 19th. Homework number 5, which is now assigned, is due the following Friday, and then the next Monday after that is homework number 6. So those 3 assignments will be what material is topics used for exam number 2. I don't even remember. The question was chapter 4, 5, 6. I don't even remember the chapters. I think chapter 6 is inner products. We may get beyond that. I don't know. I don't remember now where we're at. Chapter 4 is polynomials, I believe. Chapter 5 is eigenvalues and eigenvectors. Chapter 6 is inner products. And now I'm drawing a blank for chapter 7, but we may be there. But to make up for me being absent on Wednesday, I will be available tomorrow afternoon if that helps anyone from 1:30 to 2:30, but Wednesday I will not. But the remainder of this week, Thursday and Friday, should look the same to you. We never meet on Friday, but I do have office hours on Thursday and Friday, and those should remain the same. What I want to do is continue with chapter 6 today, and that is dealing with inner product spaces, and inner products now give us a little bit more richness to talk about vectors. And in particular, we can talk about their length or the norm of a vector, and we can also, after today, talk about an angle between two vectors. And in particular, I think we've already talked about orthogonality, and that's when these vectors are the way that we sort of think of orthogonal, 90 degrees apart. But now they, based on the inner product, their inner product is 0 if two vectors are orthogonal. So we'll look today, the main starting point will be an orthogonal decomposition of any vector u in terms of a direction v, a different vector, and a component that is orthogonal to v to make up u. So u will be a sum of two vectors, which is a scalar multiple of v, some direction in v, and then orthogonal to that to create the vector u. Then we will use that to show to derive the Cauchy-Schwarz inequality, or CSI. I don't know if that's still a show or not, but now when you hear CSI, you'll start thinking, oh sure, Cauchy-Schwarz inequality instead of the television show. But if you start texting CSI, if you're in the know, you know it's now Cauchy-Schwarz inequality, which really says that the absolute value of the inner product is bounded or is less than or equal to the norm of both vectors in that inner product. And the next line really is just using the property of absolute value, saying, oh, if the absolute value is bounded, then I'm bigger than the negative of that and less than the positive of that. That's what that second line. And now if we divide both sides by the norms of those two vectors, we get -1 and +1, and that bounds cosine of theta. So that's how we can obtain an angle from this inner product information, an angle between two vectors. We're getting some really complicated geometrical shapes. Now we're up to a triangle. We already had that, didn't we? We already figured out Pythagorean theorem last time or sometime before. Now we'll talk about the triangle inequality, which says that the length of two sides is bigger, or the sum of the lengths of two sides of a triangle exceeds or is bigger than the third side. That's really what the triangle inequality says. Then we'll pull out an envelope. The winner is the parallelogram equality. You just think about the back of an envelope, and maybe that will start helping you realize what in the world parallelogram this is an equality, the parallelogram equality, and we'll talk about that. But it doesn't have to be restricted to an envelope. You can now skew that envelope to be a parallelogram instead of a rectangle. But I like to sort of think of an envelope, and that gives me something to sort of grab onto. Then we'll talk about a different adjective in front of our basis vectors. Now we will talk about orthonormal basis, and that gives us a very rich basis to play with. And then we'll talk about the Gram-Schmidt procedure, or a way of creating orthonormal lists. You give me a list, I can now create an orthonormal list from that set of vectors, and that I'll do using the Gram-Schmidt procedure. So we have quite a few names going on, and even some geometric shapes to keep track of or to guide us today. Let's just remind ourselves of what we have. We're dealing with inner product spaces, which really is a vector space that possesses an inner product. We've added on to the vector space. Now we're saying the vector space, we're going to give it an inner product, and that inner product is not unique. We can create many different inner products, but those inner products need to have certain properties. Those properties are positivity, meaning you take the inner product of a vector with itself, that's going to be non-negative. It will only equal 0 if that vector itself is the 0 vector. That's the definiteness of the inner product. We can break apart a complicated inner product if we have a combination in the first slot. We have additivity in the first slot, and we actually showed additivity in the second slot last time. So we have additivity all over the place in terms of inner product. We also have homogeneity in the first slot and conjugate. So these are the properties that we have to have, but we derived from those that we also can think about the conjugate homogeneity in the second slot. That's not a required property, that's a resulting property of the inner product. And finally, we have conjugate symmetry. And that really only comes into play when we are dealing with vectors that have complex elements. Two vectors, u and v, their inner product is equal to the conjugate of the inner product of v with u. So those are our properties of the inner product. We also talked about or defined a norm, which is now simply the square root of the inner product of a vector with itself. And you can then derive what happens to the square of that, of the norm of a vector, if that vector is scaled. If you now have a vector u and you've found its norm, you can square it, and then if somebody says, oh, I'm scaling your vector u, you can say, oh, I know what the norm squared of that new vector AU is. And it's just using this homogeneity property, the homogeneity of the first slot and the conjugate homogeneity of the second slot, to say, oh, that's just AA star, where star is the conjugate, complex conjugate, and anytime you take a complex number and multiply it by its conjugate, you get the absolute value squared. So that now tells us that the norm of AU squared, I guess A is a scalar, so if you feel better saying UA, you can do that. You can say the norm of UA instead of the norm of A. Anyway, AU's norm squared is the absolute value of A times the norm of U squared. Orthogonality we already talked about, and what we want to do today is start with where in the world does this orthogonal decomposition come from, or how do we find this orthogonal decomposition of one vector in terms of another. So you give me a U and a V, I can say, oh, I can decompose U in the direction of V and a component that's orthogonal to V to get you to U. That's the orthogonal decomposition, and we will derive or show where these scalars A are coming from now, after this particular point. But I want to just give you this. This is now the road sign, or this is the billboard. And now we want to figure out where did that A, that's really U is equal to AV plus W. A is simply a scaled version of U, or it's a scalar, and obviously it's a very specific scalar. That scalar A is an inner product of U with V, so that's basically saying how are U and V aligned, and what component of U is aligned with V. That's the inner product, and then we're dividing, or we're normalizing that by dividing by V's norm squared. What we want to do now is figure out or get a little bit more comfortable with where that's coming from. So let's do that now. Let's start with two vectors. We're assuming somebody hands you two vectors, and what we want to do now is decompose one in terms of the other. And we are going to decompose U in terms of V and a component orthogonal to V. Or we're going to look at the question, how can we write U, the vector, in terms of V and W, where W is a vector perpendicular to V. So I'm getting lazy, and instead of writing perpendicular, I'm just going to give an upside down T. That's supposed to be representing the word perpendicular. And really, we can think about this pictorially. Suppose we now have a two-dimensional sketch of what we're doing. Suppose that we say, oh, you have a vector V, let's say there's V, and you also have a vector, let's say U. And what we want to do now is scale V by some scalar A and go only to there, and then go orthogonal to V and do a head to tail connection of these vectors and attach or add W to AV and get to the vector U. That's the thought process. So this particular stretch of the vector V is just a scaled version of V. And the scaling is A. If A is now a scalar, let's just say A is in our field, R or C. Now what we want to do is we want to say, let's write U, a generic vector U, in terms of a scaled version of V plus a component that's orthogonal to that. And in fact, the orthogonal component will actually be U minus AV, where this is now our vector W. And do you see, really, we haven't done much math on the right-hand side. We've just added 0. If you look at that, you say U is equal to U, because all you've added is AV minus AV. So we really haven't done a whole lot of math. What we want to do now is find just the right A to make this work the way that we want it to work, meaning to create an orthogonal decomposition. That's what we're wanting to do. So our goal, since this doesn't look very much, you might not want to go home and show your mom or dad, look what we did in class today. We added 0 to a vector. I'm paying how much for this education? Then you can derive this decomposition, and then they'll know that they're getting their money's worth, right? So now here's our goal. We want to find this scalar A that makes V and W, which is U minus AV. So here's W. We want V and W to be orthogonal. So now we could write that, or say that we want V to be orthogonal to U minus AV. That's what we want. And this is really just another vector that we might call W. And we now know how to find vectors that are orthogonal, or we can use our knowledge of orthogonality to figure out what A needs to be. So if V is in fact perpendicular to W, then you know what's required. You know that the inner product of W with V needs to be 0. That's the definition of orthogonality. And it's obviously going to depend in a particular situation what the inner product is, but right now we're not specifying a particular inner product. But if we have W and V being orthogonal, we know their inner product is 0, but now let's get the A in there. Right now A is buried in W. Let's put it in and say, oh, it's U minus AV inner product with V. And now we want to try to simplify that. And one way is we can use one of the properties. Additivity of the first slot. So now we can rewrite that messy inner product as a combination of two inner products. We now can say, oh, that's U and V's inner product minus AV inner product with V, and that has to be 0. That's from additivity of the first slot. And now what do we do? Now we can pull out that scalar using homogeneity in the first slot. So that now we can say, oh, that's the same as the inner product of uv minus a times the inner product of v with itself, and that needs to be 0. But this is just the norm of v squared by definition of our norm. So that now we just solve for a and we have our scalar that we were after. And we found that by enforcing orthogonality on w and v. That's where the a came from. Or now we can say that a is in fact equal to the inner product of u with v divided by the norm of v squared. And now we have our decomposition of a vector u into orthogonal components. One being in the direction of v and the other one orthogonal to v. Or, so u is now a, which we just derived. That's uv's inner product divided by the norm of v squared, scaling v. There's our a, which is just coming from our field of numbers, because what's the inner product? What's the inner product give us? What does it produce from two vectors? A scalar. And now we're just normalizing that scalar with another number, which is the length of v squared, plus, and now we have u minus a times v, which is uv's inner product over the norm of v squared v. This little piece is a again, and all of this is w. So now we have u is equal to some scaled version of v plus w, which is orthogonal to v. And the picture that we can use for that is as follows. Suppose that we now say, here is our vector v, and now we want to essentially get to u from there. Well, we could project that down. That's what's telling us really what's happening with the inner product, and this now gives us a times v. And what's this perpendicular bisector? Well, if that is AV, do you buy that minus AV is parallel to that going in the other direction? If my sketch is very accurate, this is now minus AV. And what's minus, or what's U minus AV? That's that vector, which you can translate vectors parallel to each other, and that's what this is. U minus AV, and that's your W. Where A is a special A is now the inner product of U with V divided by the norm of V squared. That's now how we can orthogonally decompose a vector into two components. Questions on that? That's sort of that is a sketch or picture of this orthogonal decomposition. If you want to be visualizing something, and if this doesn't look very intuitive, then you can sort of derive that with the picture. You can say, oh, U is AV plus W, and W is U minus AV. And AV minus AV plus U is just U. Pictured, that's what you have right there. Okay, so there is orthogonal decomposition. Let's now talk about CSI. Did everyone bring their TV guides? Is that even on anymore? CSI? I don't know. I don't watch much television. What? It's old? Must be on Netflix, because I think I hear that occasionally ringing out through the house. I don't. So now what we want to do is talk about a different CSI, but it's more important to this class, which is the Cauchy-Schwarz inequality. Here, if we start with two vectors, u and v, in our vector space V, then the Cauchy-Schwarz inequality says that the absolute value of the inner product of u with v is bounded above by the product of the norm of those two vectors, the norm of u and the norm of v. And we actually will have equality if u and v are aligned. With equality, if and only if u and v are scalar multiples of each other, is another way of saying that. Are scalar multiples. So now the angle between u and v are 0, where the angle is defined. We haven't yet gotten there, but we'll get to an angle in a minute after deriving this Cauchy-Schwarz inequality. Or you could, if you don't like dealing with absolute values, you can convert that Cauchy-Schwarz inequality and say, okay, I know the definition of the absolute value. That's really just saying I have a lower bound, which is the negative of the product of the two norms, and that's going to be less than or equal to the inner product of u and v, which is going to be less than or equal to the product of the norm of u and v. That's another way of simply expressing the Cauchy-Schwarz inequality. But typically you'll probably see it written as the first one, but that then immediately gives rise to the second one because of the property of the absolute value. So let's now show why that's true. Here's our proof. Let's start with two vectors that are in our vector space V. And we are showing this top property. The other property is just a property of absolute values. So now let's look at two cases. Suppose that somebody says, well, what if V is the 0 vector? Does that even hold? Is that Cauchy-Schwarz inequality true for the 0 vector? If V is 0, then 0 is orthogonal to anything, and the norm of the 0 vector is 0. We're saying 0 is equal to 0. That's valid, isn't it? So we can quickly get rid of or dismiss that sort of benign case or that trivial case because both sides are 0. So now let's look at the more interesting situation where we have a non-zero vector V. Now we can use the orthogonal decomposition. We can decompose U in terms of v and w, where w is also an element of our vector space, and we are going to force w and v to be orthogonal. So now we're saying w is perpendicular or orthogonal to v. If that's the case, we now know how to write u. We've just derived that orthogonal decomposition. We can say u, and now we know that v, we have to go some scalar distance of v, and we know the scalar. That's u inner product with v over the norm of v squared times v. There's our a, and we don't really need to even break down w beyond just saying plus w to show the Cauchy-Schwarz. Now we're going to go ahead and apply the Pythagorean theorem because v and w are orthogonal. So now they satisfy the Pythagorean theorem since v and w are orthogonal. So by the Pythagorean theorem, or by Pythag, no insult intended, but now we have the norm of u squared, but u is just av plus w squared. That's how we defined u now. And that, now we can use Pythagorean theorem to write that as, since v and w are orthogonal, we just say, oh, that's a squared plus b squared, that's c squared. Where a squared is now av, and let's go ahead and introduce our known parameterized form of a. That's what this is. There's our scalar. There's a, and that's times v. We're taking that squared plus w squared. That's the Pythagorean theorem. But if we have a scalar that scales a vector v, and that now is a, what can we do with av norm squared? We can pull it outside. And now what does that look like once it's outside? It's the absolute value of a squared, isn't it? So now we have the absolute value of u v's inner product with the norm of v, with that squared, and then we have the norm of v squared, which is v with v, plus w squared. So we really haven't done anything too difficult. We've just applied some of the properties that we know are true for norms and inner products. Now we can write that as uv over v squared times v squared. We have a lot of v squareds floating around. We now have v to the fourth down in the basement, really, with that first a, or part of the a, plus w squared. But what do we know about this w squared? It's a scalar, it's a number. Do we know anything about that number? Its sign, it's bigger than 0, isn't it? It's non-negative by the positivity of the inner product. So this is greater than or equal to 0 by the positivity of the inner product. And this over here was u squared. So now if we throw or drop the w, the norm of w squared from that equation, hopefully it's okay to say now that the norm of u squared is greater than or equal to the norm of the inner product of u with v squared. And what's left? We have the norm of v to the fourth downstairs, and we have the norm of v squared upstairs. So we cancel one of those squared pieces, and we're left now with the norm of v squared down below. And we can simply multiply through both sides by that number, the norm of v squared, and end up with CSI. So we'll multiply both sides. The norm of v squared, and now we have u squared v squared greater than or equal to the absolute value of the inner product of u with v squared. And if we take the square root, the positive square root of both sides, we just flip it around a little bit, and it will now appear more like what we wanted to show. And now we can see that the absolute value of the inner product of u with v is less than or equal to the norm of u times the norm of v. And that's what we were trying to show. And we didn't have to specify a particular inner product. And that's actually important if we need to use that. Now we can use any inner product we want. Required no definition of the inner product. And if this is now the case, now we can use the property of absolute values to get even more from this Cauchy-Schwarz expression. Now we can say, oh, we can lower bound the inner product of u and v with the negative of the product of the norm of u with the norm of v. And that's still bounded up top or above by the product of the norm of v and u. And if I divide all terms by that same expression, that number, the norm of u times the norm of v, I get minus 1 on the left, I get plus 1 on the right, and in the middle I have the inner product of uv divided by what I divided everything by, the norm of u times the norm of v. So now I can see that I end up with minus 1 less than or equal to the inner product of u and v scaled by or divided by the norm of u times the norm of v less than or equal to 1. And that then suggests that we could actually define an angle from that expression. We could say, oh, let's just call that expression the cosine of theta, where theta is the angle between these two vectors, u and v. So that now we can say that the cosine of theta we can define to be the inner product of u and v, how are they aligned, and divide that by the norm of u and the norm of v. Or you might have seen an inner product in the past being the inner product is now the length of one vector times the length of another times the cosine of the angle between those vectors. And that's what happens if you multiply both sides by the norm of u and the norm of v, their product. So now you have the inner product of u and v can be thought of as the norm of u times the norm of v times the cosine of the angle between them, where we're calling that angle theta. I'm kind of having fun with shapes, so let's go to another shape. Let's talk about a triangle more generically. We were talking Pythagorean, which required what? Our triangle to be a right triangle, not a left. A right triangle, a triangle that has a 90-degree angle of it. Now we are talking about a more general triangle, just a triangle in our triangle inequality. Now let's look at 618, which is discussing the triangle inequality. Again, let's start with two vectors u and v in our vector space V. Then what we can show, or that we will show, is that if we look at the length of u plus v, that's going to be less than or equal to the length of u plus the length of v. And again, you can be sketching this if you want and say, oh, here's my triangle, and now we're basically saying that the length of that third side is less than the length of the other two sides, the sum of the length of the other two sides. What if the angle's small? Which angle? So now if u and v are getting close, what do we know? If u and v are in the same direction, what are we going to get? Now that triangle sort of collapses into a line, doesn't it? And now we have the norm of u plus v is equal to, it's now equality, u plus v. Is that what you were meaning? Were you meaning that this angle is getting smaller? Oh, getting larger. What happens if it gets larger? How large do you want it? 180 degrees? Then you basically get back to what, well, depending on how long u and v are, but now u plus. So play tonight with triangles and see if now it becomes a little bit more interesting now that we can talk about triangles in terms of vector spaces and inner products. But here we have the triangle inequality, and equality will hold in this triangle inequality if and only if u and v are non-negative scalar multiples. So let's look at a proof of this. Suppose we now let u and v be an element of the vector space V. Do you see where the non-negative is coming from? If we reverse course on u and v, then u plus v is going to be a lot shorter than the sum of u plus v. If they're on top of each other, now if you walk 10 paces, that's u, and you turn around and go 7 the other way, u plus v is 3, but u is whatever I just said, 10 plus 7, that's not equality, is it? 17 is not 3. You have equality if they're aligned non-negatively. Not that one is reversing course. So that's the non-negative scalar multiple part of that. But really, you want u and v to be aligned if you want that equality to hold. So let's look at the proof of this. If we now have u plus v, the norm of that, the length of this vector, u plus v squared, you know how to write that now. Now you can go home and play with inner products, right? You can write that as an inner product. You can say, oh, any vector's norm squared I can express as an inner product. That's now u plus v inner product with u plus v. And now we can just play as much as we want with that because we know additivity of the first slot. Suppose we do that. We have u inner product with u plus v plus v inner product with u plus v. And now let's do the second slot because we know we have additivity of the second slot. Now we can say that this is u inner product with u plus u inner product with v plus v inner product with u plus v inner product with v. But now what I want to do is actually turn this around because I want to combine some things. So if I switch the slots or the vectors in the slots, now what do I have to do with the inner product of uv to make it equal the inner product of vu? Have to take the complex conjugate. Ooh. Okay, you can spend a little bit more time with your star. My star didn't take very long to develop or be created, so you can use a little bit. Okay, what do we have? We have u and u, and we have v and v, and we have uv plus uv conjugate. But what's a complex number plus its conjugate? What falls apart or what disappears? If you have a plus jb and add a minus jb, the imaginary components are gone, aren't they? So now we can say, well, this is just the norm of u squared plus the norm of v squared plus 2 times the real part of the inner product of u and v. That's adding the inner product of uv with its complex conjugate. What did we just use? Or what did we just derive? CSI? We know how to bound the inner product of u and v in terms of lengths of u and v. So this now is less than or equal to, we're just going to keep the first parts of this, but now we can say that that's 2 times, or this is really just a property of complex numbers, isn't it? I'm making it too difficult. The real part of a complex number is less than or equal to the complex number. So now the magnitude of uv. So I was getting ahead of using CSI. Right now in this step I just want to say, oh, I can upper bound the real part of a complex number by its absolute value. That's all I've done so far. So this is just using the fact that the real part of a complex number is less than or equal to the absolute value of that complex number. That's all I've done so far. And now I can apply CSI, now that I have the absolute value of the inner product. Now I can say, oh, on the left I had u plus v norm squared. That's now less than or equal to u squared plus v squared plus, should have cut my paper. Oh well. I'm going to bend it down a little bit. 2 times the norm of u, norm of v. This is from CSI, bounding the absolute value of the inner product of u with v. Maybe it doesn't quite look like it, but this is a very common algebra expression. We have u squared plus x squared plus y squared plus 2xy. Oh, that's x plus y quantity squared, isn't it? So this is, in fact, just u norm plus v norm squared. So that now, putting all of those pieces together, I can now say that the square of the norm of u plus v is less than or equal to the square of the norm of u plus the norm of v. And if I take the positive square root of both sides, I end up with my triangle inequality, which says that the norm of the third side is less than or equal to the length of the first side plus the length of the second side. And what did we specify the inner product in that proof? Did we have to tie it down to a specific inner product? No. So again, that may give us some flexibility. No definition of inner product was necessary in that development. And that's called the triangle inequality, and we can again look at a picture of what that is providing. So now if we had side 1, let's say that's u, and side 2, that's v. U plus v is where we're at now. And we can now say that the length of that third side is going to be less than or equal to the length of the first side plus the length of the second side. So here's our third side. Here's what I was calling side 1, and here is side 2. So the length of the third side of this triangle is less than or equal to the sum of the other two sides' lengths. And you could label that however you wanted, but here my picture is showing u plus v, but you could make any of those vectors u and the other one v, etc. We're playing with geometric shapes. That was the triangle. That was 3 sides. Let's go to 4 sides. Let's look at a rectangle, something a little bit more general than a rectangle, let's look at a parallelogram. And so now we can look at, with three sides we had an inequality. Now we're going to have an equality. So let's look at the parallelogram equality. Where now, if we have two vectors, let's say u and v, in our vector space v, then if we look at the sum of u and v and square that, so that's now the length of u plus v, the norm squared. And if we look at taking u minus v and squaring that, that's actually equal to twice the length of the two sides squared. So that's 2 times u squared plus v squared. That's our parallelogram equality. And I said earlier, I prefaced that with an envelope. If you turn an envelope over, on the back side you kind of have these diagonal lines on it. Well, that's what u plus v and u minus v represent, the diagonals. You take the diagonals and square them, their lengths, add them together. That's equal to the length of each side squared and doubled. So you're walking around that parallelogram. Or in pictures, if I can draw this, let's say this is now u, and here is v. So don't think this is an envelope. This is now a parallelogram. It's a bent or shifted or squished rectangle. What's u plus v? That's pretty clean defined, isn't it? That's just from where we started to the head of v. So u plus v is right there. And what is u minus v? Well, let me draw, well, how do I want to do it? I could say, if I do kind of a construction, here's a construction line. Here is minus v, isn't it? And what is this? That's u minus v, head to tail, right? So here is u minus v. But what is that? If I actually shift that, here is in fact, and now I'm probably not going to draw this very well, but here is u again, and here is minus v, so that u minus v is just translating that or parallel to that. This now is this u minus v vector. That's down there, but I've now translated it parallel so that now you see these diagonals in this parallelogram. We take their lengths, square them, and add them up. That's going to be the same as walking around that whole thing effectively with the norms squared. So that's the picture. So forget what I did with the construction and just look at the tilted back of an envelope, or straighten it up and say that's all I have is an envelope's back with the diagonals and the sides. Let's look at the verification of that, or the proof. So here's our proof. Again, we're starting with two vectors, u and v in v, And we can have u plus v squared, or the norm of u plus v squared, plus the norm of u minus v squared. And you know how to go from here. These are now inner products. So we can now say, oh, that's the inner product of u plus v with itself, plus the inner product of u minus v with itself. Now knock yourself out with additivity of the first slot and the second slot, right? Everything's additive. So I can now say, if I do this, I can say u and u plus v plus v u plus v plus u minus v plus, or let me say minus, v u minus v. Am I staying awake? Everything still okay? Let's now get rid of, or clean this up to only have two elements involved. So let's do the first piece. We now have u and u plus u and v. That's from the first one. So I should end up with 4 terms eventually. I'm sorry, 8 terms eventually, because I now have 4. Plus, I can say v with u and v with itself. That's all just accounting for that, right? Whoops, maybe I don't know how to color code this. I'm not doing a very good job, but that's what we have so far, I hope. Now what's left? Running out of colors. Let's do this one. So I now have plus u and u minus, I'm going to slide that minus because I can conjugate a -1 easily enough. And this is now u and v. And what else? Do I need to go another color? I'll do black since I haven't done black in this right-hand side of that equality, so that I now have minus v with u and a minus or a plus v with v. And I hope that now I've aligned those to show you that that goes away, as does this. And what am I left with? I'm now left with 2 times the norm of u squared plus 2 times the norm of v squared. Or that's now just 2 times, oh, I don't know why I hit the shift key, u squared plus v squared. And that's what we were trying to show, that that's equal to those diagonals lengths squared. And what did we do with the inner product? Or did we define an inner product in that development or proof? Again, we didn't. So we didn't have, note, no definition . I hope no one's getting confused with IP, intellectual property. This is IP as inner product, not intellectual property. So don't go to your lawyer and say, well, we were talking about IP all day today. Well, our IP is an inner product and not intellectual property. You're developing some intellect. Well, you're developing some intellect, I hope, after this lecture. And you decide if it becomes intellectual property with how you use it, right? All right, let's keep going. Again, I challenge you to find the Supreme Court discussion on orthogonality in your textbook, the quote, the give and take. with the Supreme Court justices. And it was based on orthogonal. And now we're switching into that. We're going to now start using orthogonal, but we're going to be even more specific. We're going to normalize those. We're going to make these orthogonal vectors have a length of 1. Now that we have length, we can talk about angle and length combined. So now let's look at orthonormal bases. Here we call a list, and I'm looking for my, never mind. I didn't say a set of vectors, I said a list, okay? So now we call a list of vectors orthonormal if the vectors are all pairwise orthogonal and each vector has a norm of 1. We know how to find the norm of a vector. Now we're going to make that equal 1. In other words, given a list, and now I'm going to call that list E1, E2. These are now vectors. These aren't elements of a vector. E1 is a vector, E2 is a vector. Do you see how I'm overusing E subscripts? But hopefully by context it's not confusing. E1 is a vector, E2 is a vector. I now have a list of M vectors. The list is orthonormal if the inner product of E sub I, E sub j is delta ij. Where delta ij is the Kronecker delta. Not the direct delta, but the Kronecker delta. It equals 1 when I and j are equal. That's the Kronecker delta. So here let me say this is the Kronecker delta is what we're using here, and the way that we're defining that, delta sub ij is defined to be 1 if the indices are the same, if I equals j and it's 0 otherwise. So now we have this list of vectors, and the list is orthonormal if we find the inner product of pairs of these, and the only time that inner product is meaningful or has a non-zero value is when you're comparing one of those vectors in your list with itself. Then it has an inner product of 1. And the reason why we're looking at this is because these are particularly useful. So orthonormal lists are particularly useful. And one result that falls out of this is the following. Proposition 25 in Chapter 6. And that says, well, the label of this proposition is the norm of an orthonormal linear combination. That's the label, or the label of this proposition. We want to know something about the norm of an orthonormal linear combination. So we're linearly combining these vectors from this orthonormal list, meaning we're scaling them by some amount and adding up scaled versions of these vectors. If we have this list of vectors E1 through E sub m, and they are orthonormal, so if this list is an orthonormal list, in our vector space V, then if somebody gives you a generic vector that's a linear combination of these vectors, let's say they say A1 E1 plus A sub 2 E2 plus A sub m e to the m. So they now give you this linear combination, and this really is just some generic vector W. And they say, oh, what's the norm of that squared? You can just say, well, hand me all your scalars, please. Give me an A1, give me an A2, give me an AM. I'm going to find their absolute value, square those, and add them up, and I'll give you the norm squared. That's what this says. So this says that you can now say that this linear combination of vectors in a list is now going to equal the absolute value of A1 squared plus the absolute value of A sub 2 squared up to the absolute value of A sub m squared for all of these scalars that are in your field. So no matter how you linearly combine this group, this list of vectors, E1 through EM, you can quickly find the norm squared using this condition or this relationship. Let's see if we can prove that in the amount of time left. It's really not that challenging, but it will maybe test your appreciation of a summation symbol. So here what do we have? We have A1 E1 plus A2 E2 plus A sub m E sub m quantity squared. But you know how to find that. It's the inner product of that mess with itself. So now I have A1 E1, A2 E2, A sub m E sub m, inner product with A1 E1 plus A2 E2 plus A sub m E sub m. Now, let me do additivity on the first slot. Right? But I can collapse that down with a summation. So I can now say, oh, I now have A1 E1 with all of these other 1 through m vectors. And I'll say that's A sub L E sub L from L equal 1 to m. And I'm using additivity of the first slot. So I need to keep doing this, don't I? I need to do that m times. L equal 1 to m with A2, E2 with all of these AL, ELs. And just keep doing that. Dot, 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 L equal 1 to m of A sub m, E sub m with A sub L, E sub L. But do you see that I can compact that? Now I can do that a second summation on the things in the first slot. And then I have homogeneity of the slots. And then I have what? The orthonormal list of vectors, so the inner products of the A sub I with A sub j, because of the Kronecker delta property, is only going to happen when those indices are equal. So this is going to collapse down to what I want, which is A1 times its conjugate plus A2 times its conjugate, and that's going to be the absolute value of A1 squared plus the absolute value of A2 squared, etc. I'll complete that after class, but I think you get the idea. I'm going to introduce another summation and then collapse that down because of the Kronecker delta property of these orthonormal vectors. We'll pick up, the next time we don't meet physically, but you're going to have a good time because you're going to be watching the orthogonalization lecture. Stay tuned.